And we're back. Hello, good people. This is the second part of Chapter 11, Analysis of Variance. We're going to talk about Tukey tests and effect sizes here. So it's best if you watched the first PowerPoint lecture on Chapter 11, the logic of ANOVA, before you listen to this one, because you need to understand the logic first. So this is intended with the assumption that you have already looked at that, and so I'm going to reference things from that first one. So let's get into it. All right, so if you remember from last time, the logic of the ANOVA, you've got three or more levels of one independent variable, because we're talking about one-way ANOVAs. So you've got three or more averages. So instead of doing a whole bunch of t-tests, you do one big f-test to begin with. And so this one big f-test tries to reject or retain the null hypothesis that they're all equal. So again, if you remember, the f-test only says it's either they're all equal or they're not all equal. It doesn't tell you where they're unequal. It just says yes or no. They all equal, they not all equal. So it's a general f-test to begin with. And so when you're looking at this slide right here, this slide is referring to a very basic setup. I think it's in page 241 of your textbook, talking about drugs and number of psychotic episodes. So if you remember from last time, if you're looking at an ANOVA summary table, you look at drugs, you can see you got your independent variable here, and you've got your degrees of freedom are 2. Your degrees of freedom are 2 is k minus 1. K is the number of levels of your independent variable. So here I can tell that my k is 3 because it's 3 minus 1 equals 2. So I know I've got 3 different drugs here going on. So I know I got 3 different levels of drugs. That means I got 3 different averages. And I've got this overall summary table. What does this mean? What you really are looking for right away, if you're gonna eventually if you're trained eye in this kind of stuff, you just look at the p at the very far right. If it's less than 0.5, then you know you've got significance. You know you reject the null. So that's what's going on here. So if you look over here at this very p, again, if you're trained eye, you look at a summary table, your eye should go all the way to the right, see a p. If it's less than 0.5, you're like, okay, great. I got something going on here. I got some non-same averages. Everything's not equal. Again, as in last time, how do you interpret this? Is that you look down here at the bottom left, you got an f of 0.1. This is your critical f value of an 8. Your obtained over here is the f. Over here on the right, you got that 11.26. This is more extreme than the 8. So if we're going to diagram it, that 8 would be, away from the curve, but 11's farther away from the middle of the curve, so that means it's in the rejection region, so that's why we reject. So we reject the null. That's the overall saying they're all not equal. That doesn't tell us where they're unequal, just says that they're all unequal. And so I told you that we're going to talk about effect sizes here. So in the next slide, let's talk about an effect size for an f-test. So here's an effect size index for an f-test. So what does that mean? We've already been talking about effect sizes, and I want you to make sure that you guys keep up with the idea of the effect size. So you got an effect size index for an R, a correlation 0.1, 0.3, 0.5. The negative or positive doesn't matter. If you got a negative 0.5, you still got a large correlation. You got D, lowercase d, is an effect size for averages. So if you're looking at the difference between two different averages, then you got a lowercase d, and that's 0.2, 0.5, 0.8 for small, medium, and large. And now there's another effect size index for an f. And I'm pretty sure, I don't know, do I want you to remember? I really don't want you to remember this. So I'll probably give you this at some point, or you can look it up in your book if there's ever a quiz question on it. I don't want you to memorize the effect sizes for f, because now you got a 0.1, 0.25, and a 0.4, so now you got another different levels, and I think an effect size for an f is probably the least useful effect size that we've talked about, so I don't think you really need to know what is going on here, because what is it basically saying? It's just saying that at that general f test, they're all equal, they're not all equal, that the effect of that inequality is either small, medium, or large. So if we're talking about these drugs, So you've got three drugs, and the three drugs having an effect on psychotic episodes. Again, I'm on 241, page 241 in your textbook. Psychotic episodes. It just is telling you that there is a small, medium, large effect of the drug on psychotic episodes, which is kind of cool. But the problem is I don't know which drug is having the effect or not. It just says drugs do. Well, it might just be drug number 1. It might just be drug number 2. It might be just drug number 3. I don't know that yet because I haven't gone into the specifics yet. I've only been at a general F-test level. It just says they're all not equal. All right, well, what does that mean? Well, that means they're all not equal and drug has this effect. But it doesn't tell me which drug does have an effect, which is kind of important if you're thinking about drugs. You kind of want to know which one is the one that's causing the difference, not just the drug in general. So that's why I don't really love this F test, because it's not specific enough for you. But I need you to understand, because it's part of this class, that there are effect size index for F. So if you see an effect size index for an F, basically know that, yay, you found an effect size. If you're reading a journal article, you'd be like, oh, yay, we found something. But at the end of the day, what you really are going to care about is which specific drug had a significant difference between another drug and what the effect size for that was. And so if you're going to be comparing averages, so drug A versus B, drug B versus C versus A versus C, those are lowercase d effect sizes, which you're probably going to be more interested in it, because if you find out if drug C is really what's going on, then you want to know the effect size of drug C relative to drug B, or drug C relative to drug A. So that's what we're talking about with a lowercase d if you've got two averages. This is an overall F test effect size for, drug has an effect on, but you don't know which one. So it's really I just need you to know it's out there. I'll give you this 0.1, 0.2, 5.4 to help you interpret. But other than that, I just kind of just need you to be aware. Okay, so if we were on page 241 in your textbook asking about these drugs and psychotic episodes, if you turn the page on 242 and 243, oh God, and just everywhere, honestly, you see a whole bunch of equations that I don't want you to spend a lot of time dealing with. I need you to understand the logic of ANOVA. I need you to understand how to interpret an ANOVA table. I need you to understand how to interpret the results. What I don't need you to do is calculate sum of squares, total sum of squares, treatment sum of squares, error sum of squares, mean sum of squares, all that kind of stuff. So you might just want to not spend too much time on all that kind of stuff. But what I do want you to understand is if on page 247, that's where we're seeing the exact same summary table that we just talked about in the last slide. But what to get more specific with an F test is that you got to find out the differences between the averages of all levels of the independent variable. So what does that mean? So if I was in class, I'd be drawing this on the board. So you're going to be able to compare means. You're going to be able to compare drug A mean versus B. You're going to be able to compare A versus C. You're going to be able to compare B versus C. So if you've got three levels, how many comparisons are you going to have? You're going to have A versus B, A versus C, B versus C. So you're going to have three different comparisons there. I also need you to understand how that's going to go crazy if you add a fourth. So let's just say you add a fourth drug. So you got A, B, C, D. So now you have A versus B, A versus C, A versus D, B versus C, B versus D, C versus D. So now you got a whole bunch of other now comparisons. So it kind of explodes exponentially as the number of levels of the independent variable you get. That's what you're kind of going to be interested in. You're like, all right, well, I want to know the differences between these averages. Well, I need you to understand sort of the statistical terminology about those comparisons between those averages. So that's what this slide is talking about, comparisons among means. I need you to understand the difference between a priori and post hoc. So a priori, that's what the second bullet point is here, the a priori, basically says that you had an idea that one drug was going to be better than the other drug or all the other drugs or whatnot. So in this example, in your textbook, it sounded like the researcher believed that drug C would be better than drug A or B. So if you have that belief, if you have that, that's sort of like your research hypothesis. That's your experimental hypothesis. And so a priori would be is making the statement, I expect C is going to be better than A or B. And so that's an a priori comparison. So what does that mean? That means you're having stronger research. You're going to have a one-directional hypothesis, that sort of thing. So that's an a priori. Post hoc is basically like, I don't know what I'm doing. I'm just going to compare all the means to each other. So let's go back to this idea of what I just said. If I had 4 levels of independent variable, A, B, C, and D. So post hoc would be, all right, I don't know what I'm doing. I'm just going to compare all the means. I'm going to do A, B, A versus B, A versus C, A versus D, B versus C, B versus D, C versus D. I don't know. I'm just going to look at them all, see what happens. It's not very strong research logic. It's not very good research. You'd be like, you don't know what the hell you're doing. You're just casting a big net, shooting in the dark, seeing what you'll hit, that kind of stuff. A priori is much more research oriented. It's much more believable, and that kind of stuff. So if somebody believes that drug C, it's kind of this idea. Drug C would be, hey, there's this new drug to treat, I don't know, let's say schizophrenia, and we've got the 2 old drugs, A and B, that aren't that great. We don't love them, whatever. And this new drug C is that we're really trying to figure out. We believe C is going to be different from A and B. That's kind of what the research would be. Is that you've got to test this new drug compared to the other old drugs. That's what this could be. What a situation where we have A versus B versus C. So a priori just means you know which plant comparison you're going to look at before you even look at the data. Post hoc is that you just look at whatever after the data happens, which is kind of, it's not very strong research. That's all I'm saying. Either way, you got to run a Tukey honestly significant difference test. So this is why it's called a Tukey, HSD. So this is a option that you select in SPSS that gives you another table that we're going to see here in a second. That's what I need you to interpret when it comes to the individual differences between averages of each level. Okay, so let's talk about a Tukey test. So if you look here, Tukey test is basically one average. This up here, you got x bar 1 minus x bar 2 divided by the error term. So you've got, it's just a difference between 2 different groups, group 1 versus group 2. Always works with equal sample size. If you got different sample sizes, it gets kind of weird. You can look up critical value. In Table G in Appendix C, if you're interested, that's where we find critical values for a honestly significant difference tests. I'm not going to ask you to do that. What I am going to ask you to do is if you can understand what a significant Tukey test looks like. And it's going to be based off of a summary table or planned comparisons table, a Tukey table that we're going to see in the next slide here, and I need you to understand how to interpret that. So if you look at this 4th bullet, works the same as previous. Your honestly significant difference value is greater than the critical. You reject the null, say the 2 means are statistically significant. Give me directions, means, and p-values. All right, so we're going to use this example again from the book about the 3 drugs. So click on the next slide. Okay, so here is SPSS and different statistical programs have slightly different looking output, but in general, this is what the output is going to look like. So up here, you'll see multiple comparisons. What does this mean? You're comparing multiple means. Dependent variable, sometimes if you label your variable, it'll come up here. This is psychotic episodes. It says Tukey, honestly significant difference test, which is kind of nice. So now you know you're dealing with a Tukey test. And so this is what's going on. So let's spend some time figuring out how to interpret this table here. So if you look over here on the left, you got A, B, and C, and then you've got drug over here on the next column. So if you look across in this row, you got A versus B. The mean difference is 0.5 between those two. So if you look up here, if you say A is I, the independent, or I don't even know what this I stands for. So you got A equals I, B equals J. So this is what this I minus J looks like. So A minus B equals 0.5. So which is telling me that A is 0.5 higher than B. Got the standard error, which is great, whatever. You kind of want to look right here to begin with, significance values. You're always looking for less than 0.5. Less than 0.5 equals significant difference. This is nowhere near less than 0.5. This is almost 1. This is almost the exact same number because it's only a difference by 0.5. So this is nowhere near significant because this is nowhere near less than 0.5. This is 0.9 as opposed to less than 0.5. So what does this mean? This means this is not a significant difference. A and B are not significantly different. So what does that really mean? In theory, that means A is equal to B. They're not significantly different enough to say that they're different, so we basically treat them as the same. Drug A is basically the same as drug B. So now you go one more row down here, you got A versus C. A versus C, the difference is 5. You're like, okay. And what's kind of nice is that I don't know if you've noticed, but you get asterisks, whatever, whenever you see something that's less than 0.5. So if you look at the significance level over here, you got 0.005, that is way less than 0.5, it's less than 0.1. And now we know that it's significant because they give us a nice little asterisk here. And so right now, I know there's a significant difference between A and C. And I know that A is 5 higher than C. How do I know that? Because I got a positive number here, 5. So this one has to be higher than that one. So we look at this next row, B versus A. It's the exact same thing as A versus B. It's just flipped around. That's why we got a negative sign. That's why we got the same standard error. That's why we got the same significance level. We got the same sort of confidence intervals. They're just in different directions. So B versus A is the same as A versus B. So A versus B is here. A versus C. The only new one is B versus C. And so now we got a B versus C right here. Got another asterisk. Less than 0.5. Difference is 4.5. So what does this mean? We've got another significant difference here. So what is that saying? If you were going to write this on the board, like I wish I wasn't in class. If I was going to write this on the board, we would say A is equal to B. A is not equal to C, and B is not equal to C. So that's what this is telling us here. I've got a significant, A is equal to B, C is not equal to A, and C is not equal to B. So basically you're telling me C is significantly different from the other two. Okay, so when you first look at this whole thing, probably should look at the significance. You find something that's less than 0.5. It'd be super awesome if there's asterisks there. If there are, it's basically highlighting where you should be looking. A is not equal to C, B is not equal to C, A is equal to B. If you want to look at this very bottom here, we've got a C, obviously is not equal to A or B. That's why I got 2 asterisks here. So there's a lot of repetitiveness in this table. All right, so that's one thing I want you to understand from this graph. The next thing is this confidence interval. So what I need you to understand is confidence intervals of mean differences mean that the difference between these two groups are found within this confidence interval. So let's go down here, C versus A. There's a difference of 5, like a real difference. So that whatever the average of C that we got, the difference between the average of A is actually 5. But over here I've got 95% confidence interval. So what does that mean? That means I'm 95% confidence the real difference between all people that could be in group A, all drugs, all people who take drug A versus all people who take drug C, the difference is always going to be between 1.7 and 8.2. And you're like, well, what is this? This is a negative number. It's just because it's on the other side of the 0 on the number line. If you look up here, A versus C, it's the same thing, 1.7 versus 8.2. So there's always going to be a difference. The difference might only be 1.7, but there's always going to be a difference. It's either going to be 1.7, it could be up to 8, which is a bigger difference than just 5. So I'm 95% confident the real difference lies in here. So what does that mean? There's always going to be a real difference. Let's look up here on this A versus B. If you were going to plot this on a number line, -2 would be on one side of the 0, and then 3, positive 3 would be on the other side. So what does this mean? If you're going to plot this on the number line, there would be a 0 here. So if you're going to go -2, -1, 0, +1, +2, +3, there would be 0 in this confidence interval. If I'm saying that there's the possibility of a 0 between these two groups, I'm 95% confident that there's a possible 0 difference between these two groups. That's why I'm not finding significant difference here. Because I'm 95% confident that 0 could be an option, and if 0 is an option, that means there's no difference, which means you shouldn't say that they're different. You can't reject the null. The null is that they're equal, and if 0 is in your confidence interval, then you're basically saying that they can be equal. And if they can be equal some of the time, then you can't say that they're different. That's what this is all talking about. So if you look at this next row, this A versus C, I'm confident, 95% confident, that the difference is always going to be around a 1.7 to an 8.2. 0 is never in there. So if 0 is never in there, I know they're always going to be different. If they're always going to be different, that's why I'm able to reject. So it's very common to see if you've got a significance difference test, like here, this 0.005, that you know 0 is not going to be your confidence interval. If you see a 0 in your confidence interval, you're going to be, okay, if 0 is a possibility, that means they're equal, and that means you can't reject, which that means you have to retain that they are equal. So that's why I need you to understand how to interpret this confidence interval area. If 0 is in it, that means there's a possibility of no difference, meaning that they're the same, meaning you retain. If there is no 0, then that means you probably should be rejecting that they're always going to be different. That's what I need you to understand from this test, or this table. So spend time in Chapter 11 and Chapter 13 focusing on how to interpret result tables. The overall F-test ANOVA summary table and the Tukey comparisons table. And so there's going to be a lot more writing involved in Quiz 6 and Exam 3 because I'm just going to be handing you a whole bunch of these pictures, and then I'm going to ask you to explain and tell me what you know about this. There's going to be very little calculation. All right, so this is how we do multiple comparisons. This is how we figure out a table for how to discriminate between these two, all these different averages, possible combination of averages. And so finally, the effect size for those paired comparisons is going to be the same thing we've been doing before. We got lowercase d, we got the difference between the two different averages. We divide it by this an error term. The error term is this term. Again, look it up in the back of the book. I'll give you this error term, or I'll give you the equation in order to calculate this error term. So this is it, and then you interpret it the same way. The 0.2, 0.5, 0.8, that lowercase d. So if I wanted to know, so from the last slide, we just said that C is significantly different from A and B. Well, how big are they? Well, how big is that? I know they're significantly different. Well, how large of an effect is having C on my symptoms rather than B, taking drug B? That's what I'm looking for when it comes to an effect size. So calculate an effect size, and you might be saying, ooh, there's a large effect. There's a large effect on psychotic episodes if you take drug C rather than taking drug A. There also could be a large effect if taking on episodic episodes if you take drug C versus if you take drug B. That's what I kind of want to be able to see here. And so there's no point in doing effect size index between retain, hypothesis, paired comparisons. All right, you might want to have to rewind that one. So if you've got A, if we say that A is equal to B, there's no point in trying to find out the effect size between A and B if you're telling me they're the same, because there is no effect of being on one versus the other because you just told me they're the same. So you should really only be calculating effect sizes for significant differences between means. So I wouldn't expect you to calculate an effect size between A and B because it's the same. I would expect you to calculate an effect size A versus B, A versus C. I'm sorry, B versus C and B versus A, because that's where we found significant differences. So calculate effect sizes only for significant differences between averages. And again, we'll go through some of this. I'll post some worksheet videos that we can go even more specific into examples, but this is sort of what I want you to be prepared for when it comes time to look at the worksheets. I think that's it. If it is, thanks for listening. Keep watching. If it's not, then I'll talk over the next slide.